Alrighty, good afternoon. This is period A4. This is Precalculus CP. I hope you're having a great day so far, and this will cap off not only the day, but the week of classes, so I hope that that goes well for you. I want to remind you that tomorrow is a vacation day, as it's scheduled. It is not a day that you have to report for attendance, so I do hope you enjoy your day. That being said, there will be, as our usual pre-calculus routine dictates, a progress assessment being sent out to you via email right at the end of this class. It's scheduled to go out at exactly 1:30 p.m., so you should be receiving it then. What that progress assessment entails is 5 problems based on your double angle identities. There are 2 problems on simplifying, which is just kind of like what we did the other day, where we just very straightforward apply the identity to simplify an expression. 1 triangle problem like we did last class, and I want to start out with another triangle problem today just to make sure we review that. And then 2 proofs. And today I have 4 proofs lined up for you that I want to show you involving the double angle identities. All right, so that's really what's coming up. Again, that progress assessment will be sent via email after class, and you are expected to have it done and submitted to me by 11:59 p.m. on Sunday night. All right, so that gives you Thursday afternoon, all day Friday, all day Saturday, all day Sunday. Should be more than enough time to get it done and submitted. All right. If you do have any questions at any point, please feel free to just send me a little message, either Google Hangouts or whatever. Just let me know. I'll be happy to jump on Google Meet with you if I can and see what's up. All right. Tomorrow, my AP Computer Science class has their AP exam, so I'll be, a little worried about that with them. I think they'll do well, but I'm still like, oh, I hope they do okay. So I'll be probably pretty occupied with making sure they're ready and answering questions, but that doesn't mean you're going to get left out, of course. Please just send me a message. I'll be happy to help you out in whatever way I can. All right, so anyway, let's go ahead and jump right in. We're going to start with a problem that says, like a triangle problem, like we did last class, if angle A is acute and the cosine of A is 4/5, let's find these other things. Well, first of all, recognizing that angle A is acute, an acute angle is, of course, less than 90 degrees, which would therefore mean that our angle is in the first quadrant. Right? It's in quadrant 1, which goes from 0 to 90. So drawing our triangle would look like this, starting in the middle of our circle, go up and to the right into quadrant 1, because that's where quadrant 1 would be located. Draw a right triangle. This is angle A right here. And if the cosine of A is 4/5, how do you define the cosine in a right triangle? Well, cosine is adjacent over hypotenuse. So I would say it's the adjacent of 4 over the hypotenuse of 5. Okay? Now, in order to find all of the rest of those things, you're trying to find sine of 2a, cosine of 2a, tangent 2a. We definitely need to know what this opposite side is equal to. We need to know the measurement of that to find sine, because sine is opposite over hypotenuse. So we can find that no problem with a little Pythagorean theorem. If we call this y for now, we could say 4 squared plus y squared is equal to 5 squared. A little quick algebra, we can say that 16 plus y squared is equal to 25. Subtract 16, y squared is equal to 9, which means y is equal to 3. So that means that this distance right here is equal to 3. Now that I know that, we could say that, well, the sine of A, opposite over hypotenuse, the sine of A would be equal to 3/5, opposite over hypotenuse. Now we have cosine of A, we have sine of A, we have all the information that we actually need in order to find these things, right? Let's start with the sine. Just to review, the sine of 2a, according to our double angle identity, if you notice I added them to the sidebar way at the bottom there, double angle identities, is defined as 2 times the sine of A times the cosine of A. Okay, that's the identity. The sine of 2a is 2 times sine of A times cosine of A. We know sine of A, we just found that, that's 3/5, and we know cosine of A, we just found that as well, that's 4/5. So we could just go ahead and plug them both in. We could say, well, this is 2 times the sine of A, which is 3/5, times the cosine of A right here, 4/5. And using our handy dandy calculator, you don't need to use a calculator, but it certainly makes it much more convenient. We could say that this is 2 times 3/5 times 4/5, and get 0.96, which converts to a fraction of 24/25. Okay, and that would be the exact value for the sine of 2a. For the cosine, it's done in a similar way, though keep in mind with cosine, you do have 3 choices as to the variation you want to use. The cosine of 2a is defined as the cosine squared of a minus the sine squared of a. That's just, again, the identity. But another couple variations of that are, you could also say that that's 2 times cosine squared of a minus 1. Or you could say that that's equal to 1 minus 2 sine squared of a. When we do proofs in just a little bit, one of the challenges, it's not a big challenge, but one of the challenges is figuring out which variation of this double angle formula do you actually want to use in your proof. And we'll talk about that a lot more going forward, but it's like, do I want to use this version? Do I want to use this version? Do I want to use this version? Sometimes it won't even matter. You can get the correct answer regardless of which one you pick, but certainly it makes it a little easier to choose one over the other. So we'll talk about that when we get to proofs. For our purposes in this triangle problem, though, we can really pick whatever variation we want. Typically, I always go with this just default representation right here, cosine squared minus sine squared. So that's what we're going to use. But if you prefer to use this or you prefer to use this, that's fine too. You'll get the same answer. So I'm going to say that the cosine of 2a is cosine squared of a. Well, cosine of a is 4/5, so I'm going to do 4/5 squared minus sine squared of a. Sine is 3/5, so 3/5 squared. And plug it into a calculator. Let's see what we get. I get 4/5 squared minus 3/5 squared, and we get 0.28, which as a fraction is 7/25. Just like that. Okay. Last but most certainly not least, with a problem like this, we're now looking to find the tangent of 2a, which at first glance you might be like, but Mr. Giorgio, we didn't talk about the tangent formula. How am I supposed to do that? But then you think about your quotient identity. It's right below where my finger is, right there. The quotient identity, you would say, oh, the tangent of 2a is the same as the sine of 2a over the cosine of 2a. And we know what the sine of 2a is. We just found it. We know what the cosine of 2a is. We just found it. We can say that that's 24/25 divided by 7/25. How do we divide by a fraction? We don't panic. We multiply by the reciprocal. We get that this is our first fraction, 24/25, times the reciprocal, 25/7. 25's cancel out. And so the exact value for the tangent is 24/7. Okay. Any questions, comments, or concerns about that at all in the slightest? Nothing? Seems like we're A-okay. If you do have anything, though, please feel free to speak up, and please feel free to type it in the chat if you do have anything. But that's how you do one of those problems. That's what you can expect on your progress assessment. All right, let's jump into the proofs then. Let's jump into the proofs if nobody has anything. Again, feel free. Don't feel like you're interrupting or it's rude or anything. Just speak up. All right, let's go into the proofs. So, as I mentioned, one of the big problems with the proof, or that's not really a big problem. I don't want to make it seem like it's this huge roadblock, but one of the main points with the proofs is trying to figure out which of the cosine identities to use. When you encounter sine of 2a, there's only one choice, but you can make that. But when you encounter cosine, there's 3 different choices. So I'm going to try to walk you through as best I can my mentality for why I choose one variation of that cosine over the other. Like I said, I don't want to say always because I'm not 100% sure if that's true, but I will say most of the time, if not all of the time, it doesn't matter which of the variations you pick, you can still get the correct, you can still complete the proof regardless of which cosine variation you pick. But certainly some are much easier to deal with than others. So I'm going to try to walk you through and explain why did I pick this version of cosine of 2a versus another version. So let's start with our first proof. We got 1 minus cosine of 2x all over 1 plus cosine of 2x is equal to the tangent squared of x. Okay? And I'd like to prove that that's true. So we want to prove that that's the case. Well, what I can do is I can work with that left-hand side. And we're immediately faced with that choice. We have cosine of 2x here and cosine of 2x here. Which version of cosine should I use? Well, what I would realize is I would look at my goal and I would say, my goal is to get tangent squared. Tangent, you may remember, is sine over cosine. That's the quotient identity that goes with tangent. So since tangent has a numerator of sine and a denominator of cosine, when I'm converting these two things, I would probably want to convert this one using the sine variation. That's going to be the 1 minus 2 sine squared of a, or 2 sine squared of x. And I'd want to convert this one on the bottom using the cosine representation. That's going to be the, 2 times cosine squared of x minus 1. Okay? So that's my logic for doing that, because tangent is sine over cosine. Now, if you pick different things, it would certainly still work out. You just have to go through more steps. By looking at your goal, hopefully it gives you a good indication as to, let's try this. And don't be discouraged. If you try one of them and you seem to not be making any headway, it's okay to backtrack and say, let's try maybe a different variation of cosine of 2a and see if we can do anything with that. So with this problem in particular, I'm going to say, let's replace cosine of 2x in the numerator with the sine variation, 1 minus 2 sine squared of x. And let's replace the cosine of 2x, the cosine of 2x variation in the denominator with the cosine version. That's going to be 2 times cosine squared of x minus 1. Okay. Now, this negative sign in the numerator is going to distribute here and here, right? So I'm going to simplify this down to be 1 minus 1, convenient, plus, because it's going to be minus negative, 2 sine squared of x, all divided by 1 plus 2 cosine squared of x minus 1. And hopefully you start to see all the little pieces coming together. The 1 minus 1 cancels out in the numerator and in the denominator. 1 minus 1 is 0. So you're left with, just continue it right up here, you're left with 2 sine squared of x over 2 cosine squared of x. The 2's would go away, and you would recognize that sine squared over cosine squared is the same as tangent squared of x, which is equivalent to that right-hand side. And so our proof is done. Does that make sense to everybody, how that's done? Now, again, I want to emphasize that you could have picked other variations of cosine of 2x, and you still could have gotten the right answer. Let me show you. I'm going a little rogue here, but let me show you. What if you used, in both the numerator and denominator, the cosine squared x minus sine squared x version? What if you used that definition instead? Well, going from this step, you would have gotten 1 minus cosine squared x minus sine squared x. That's just the other version right here, right, of cosine of 2x. Over, and say I use that same version in the denominator, 1 plus cosine squared x minus sine squared x. Right, I'm looking at right here. What if I decided to use this variation? Well, what we would see is in the numerator, this would come out to be 1 minus cosine squared of x minus sine squared of x. In the denominator, 1 plus cosine squared of x minus sine squared of x. Take a look at what we can then do. We can apply our Pythagorean identity to say, oh, 1 minus cosine squared, that's sine squared, right? Look at the first Pythagorean identity in that sidebar there. 1 minus cosine squared would be sine squared. So in the numerator, I would get sine squared of x minus, wait a minute, why am I not at a, oh, sorry, I wrote this incorrectly. The negative is going to distribute there, so we're going to get a plus sign right here. Sorry about that. Let me just backtrack. Up here, when I replace this cosine squared of x minus sine squared of x, I made the mistake, I hope you don't, because I just did, of forgetting to distribute this negative. It would be negative cosine squared minus negative, so plus sine squared. So that's a plus. So in the numerator, I would get sine squared of x plus sine squared of x. Over in the denominator, I can replace 1 minus sine squared with cosine squared. That's a Pythagorean identity. So I'd get cosine squared of x plus cosine squared of x. And then it would all come together back to this step. Sine squared plus sine squared is 2 sine squared. And then cosine squared plus cosine squared is 2 cosine squared. And we're right back to this point here. So by picking the other variations, you can still complete the proof. Sometimes it may require more steps or maybe fewer steps, but it should be possible. Okay? That definitely requires a little more finessing though. Any other question about that before we move on to another one? I have 3 more proofs I'd like to show you today. All right, let's make it happen. Let's make it happen. How about something like this? Ready? Let's try to prove that 1 minus tangent squared of x over 1 plus tangent squared of x is equal to the cosine of 2x. Okay? Here, what I would like to do is I would be tempted to work with that left-hand side to make it look like one of the variations for cosine of 2x. Okay? So that's what I'm going to try to do. I'm going to try to manipulate that left-hand side and make it look like either sine squared minus cosine squared or sorry, other way around. My fault. Make it look like either cosine squared minus sine squared. That's the first variation of cosine 2x. Or 1 minus 2 sine squared of x, or 2 cosine squared of x minus 1. I want to make it look like either one of those 3. Which one of those 3 is going to come up? We're just going to have to see where this takes us. So let's work with that left-hand side. In the denominator, take a look at what we got going on. 1 plus tangent squared of x is a Pythagorean identity, right? You see it in that third line on that sidebar there under Pythagorean identity. That's the same as the secant squared. So I can say we have 1 minus the tangent squared of x over the secant squared of x. And that's done via the Pythagorean identity, right? We can then say, oh, well, I have 2 things here, both being divided by secant squared of x. I can split that fraction apart and rewrite it as 1 over secant squared of x minus tangent squared of x over secant squared of x. Right, do you see that? We can break that fraction apart because this is 1 over secant squared of x minus tangent squared over secant squared. So we can just break that fraction apart just like that. What that allows us to do is that now allows us to say, let's express this all in terms of sine and cosine, and then it might be a little clearer as to what happens here. Check this out. I have 1 over secant squared. Well, secant squared is 1 over cosine squared. Right? Now I have tangent squared is sine squared over cosine squared. And secant squared is 1 over cosine squared. Now I have my good old divide by a fraction thing going on here. So how do I divide by a fraction? I multiply by the reciprocal. I'm going to do that with the first term here. I'm going to get 1 times the reciprocal, cosine squared x over 1, minus multiply by the reciprocal. We got sine squared x over cosine squared of x times the reciprocal cosine squared of x over 1. Take a look at what happens after that. Cosine squared of x goes away. Here I get cosine squared of x minus the remaining sine squared of x. And look at that. The planets have aligned. Everything has all come together. That's one of the derivations of cosine of 2x, right? Or that's one of the variations of it, right? So I can just say, well, that's the same as the cosine of 2x, which is the right-hand side. And so therefore my proof is done. Does that make sense to everybody, how that's done? Cool. All right, 2 more to go. I need a fresh sheet of paper, then we'll keep going here. Bring out a fresh sheet. There we go. All right, here we go. How about something like this? I like this problem a lot. I mean, I like all these proofs. But this one in particular, I think is really cool because it uses both the sine identity and the cosine identity. We got 1 plus sine of x minus cosine of 2x. And I want to prove, over cosine. I'm getting ahead of myself. That's why I'm so excited. Cosine of x plus sine of 2x. And I want to prove that that's all equal to the tangent of x. Okay. So I got 1 plus sine of x minus cosine of 2x over cosine of x plus sine of 2x. And I want to prove that that's all equal to the tangent of x. If we're picking which side to work from, I think it goes without saying we're going to work from that left-hand side. And let's see where we can go. All right. So Once again, I would apply my logic here for the tangent, and I would say, well, our goal is tangent. Tangent has sine in the numerator, and also there's other terms with sine in the numerator already, so that would lead me to use my version of cosine of 2x, that is 1 minus 2 sine squared of x. Okay, that's what leads me towards that. The fact that, number one, tangent is sine over cosine, so I need sine in the numerator. And number two, there's already terms with sine in the numerator, so let's just make terms with more sines in the numerator. Why introduce a new thing if we don't have to? So I would rewrite this up at the top as 1 plus sine of x minus. Here I have cosine of 2x. I'm going to rewrite that as 1 minus 2 sine squared of x. Notice how I put it in parentheses because that negative is going to distribute to everything. Very important. All divided by cosine of x plus, now sine of 2x only has one choice. That's nice and easy for us. That is defined as 2 times sine of x times cosine of x. Alrighty? That's the identity we just applied. Now, let's see how we can rewrite everything. In the numerator, I have 1 plus the sine of x minus 1. Notice minus negative. This is the mistake I made a little bit ago. Don't make it again. Everybody gets 1, right? I get plus 2 sine squared of x all over cosine of x plus 2 sine x cosine x. Not going to touch that quite yet. Notice in the numerator, the 1 minus 1 would cancel out. That would leave me with sine of x plus 2 sine squared of x all over cosine x plus 2 sine of x cosine of x. Now at this step, you may have to think about what to do next. Might be not super obvious, but what you could actually do is you could take out a greatest common factor in the numerator and greatest common factor in the denominator. Something you may be tempted to do, and please don't. It's what we in the math world usually refer to as cherry picking, where you're just going to cancel out things because it's convenient, not because it's mathematically sound. Don't just do, oh, 2 over 2 cancels, sine over sine cancels. That doesn't cancel out right now because there's an addition here, right? This is one singular term. This is one singular term. We can't just start crossing things out randomly. What I can do, though, is I can take out a greatest common factor in the numerator, and I can take out, that would be sine of x, leaving me with 1 plus 2 sine of x. See that? If I take out a greatest common factor of sine of x in the numerator, I'm left with 1 because sine of x divided by sine of x is 1. And I'm left with just a regular old sine here because it was sine squared. I took 1 away and I have 2 sine of x. In the denominator, I'm going to do a very similar thing. The greatest common factor there is the cosine of x. If I take out a factor of cosine x from this, I'm left with 1. And if I take out a factor of cosine x from this, I'm left with 2 sine of x. And now it's all coming together. Now the magic is happening. 1 plus 2 sine of x over 1 plus 2 sine of x goes away. I'm left with sine of x over cosine of x, which we know is the same as tangent of x by our quotient identity. And so we're done. Okay? Any other questions or comments about that? All right, we got one more. One more coming your way. Here we go. Ready? How about something like this? This is the last one. Let's do the sine of x times the tangent of x plus the cosine of 2x times the secant of x. And we want to prove that that is equal to the cosine of x. Okay, so we want to prove that. All right. This problem is a really good one to end on because there's a lot of stuff going on. You got sine, tangent, secant, a double cosine in there. There's a lot of factors happening. Before I actually go ahead and expand out that cosine of 2x, I actually will do some simplifying first. I think it would be much, see how there's so many different functions here? I think it's much actually easier, it saves us a lot of effort, to convert everything first to sine and cosine. If I do that, watch what happens. I'm going to rewrite this, working with the left-hand side, obviously. I'm going to rewrite this as sine of x times tangent is sine over cosine. That's our quotient identity. Plus, we'll leave cosine of 2x alone for now, times secant. Well, secant is 1 over cosine. Okay? Notice that now allows me to write this as sine x times sine of x is sine squared of x over cosine of x, plus, here I have cosine of 2x over cosine of x. Cosine of 2x over cosine of x. And now that both of these terms have the same denominator, we can go ahead and stick them together. And we can write this now as sine squared of x plus cosine of 2x all over cosine of x. And now that we've condensed things, it would be beneficial to expand out the cosine of 2x. In my opinion, which one do you think is going to work out the best? Well, we have a sine squared of x already here. So if we made this cosine squared of x minus sine squared of x, do you notice that those sine squareds would just go away and you'd be left with cosine squared over cosine, which would become just regular old cosine. I'll write it out so you see it. But that's why I would think that. I would look at all three options. I'd be like, wait a minute, this already has a sine squared. We can cancel it out with a sine squared and get just cosines, which is what we're aiming for. So notice, I would say, let's do that this is sine squared of x plus, we'll replace this with cosine squared of x minus sine squared of x. That's our identity for cosine of 2x over cosine of x. As I just indicated to you, sine squared of x minus sine squared of x goes away. You're left with cosine squared of x over the cosine of x, which is just cosine of x. It's now equal to your right-hand side, and so therefore we are donezo. Okay? I know it's 1:30, and if you have to go, you can go. Absolutely, no judgment at all. But one thing I do want to show you is I do want to show you that you could actually use the other variations as well and still get the same answer. Say at this step, right, instead of using my cosine squared minus sine squared, say I converted it instead to 2 cosine squared of x minus 1. Well, what that would look like is that would now look like this. It would be sine squared of x plus 2 cosine squared of x minus 1 over cosine of x. A little tricky to see where you would go from there, but what we could do is we could take sine squared, and you could recognize that, ooh, sine squared of x is the same as 1 minus cosine squared of x, right? That's your Pythagorean identity. So you could say, well, this is the same as 1 minus cosine squared plus 2 cosine squared minus 1 over cosine of x, right? We just replaced the sine squared with 1 minus cosine squared. That now allows us to say, ooh, well, 1 minus 1 is going to go away. I now have negative 1 cosine squared plus 2 cosine squared makes positive 1 cosine squared of x over cosine of x, and gets us right back to this step here. Okay? Lastly, we most certainly could take something like this, and instead of replacing it with this one or this one, we could replace it with the last one. What if we replace it with 1 minus 2 sine squared of x? Well, then it would look like this. We'd have sine squared of x plus 1 minus 2 sine squared of x all over cosine of x. Well, we have sine of x minus 2 sine squared of x minus 2 sine squared of x is negative 1 sine squared of x over cosine. And again, our Pythagorean identity tells us that 1 minus sine squared of x is the same as the cosine squared. So I just get right back to that same step of cosine squared of x over cosine, which is cos x. Okay? So regardless of which one you pick, you would still be able to arrive at that correct solution. I certainly think that this one is the easiest way to go, but all three solutions are equally valid. All right, which is super cool. So if you have any questions or concerns, please feel free to reach out. You should have already, as of 2 minutes ago, received that progress assessment. I appreciate you staying just a couple minutes after. It really means a lot. If you do, again, have any concerns, please contact me and let me know. Other than that, thank you for listening today and for your attention and focus. We will be continuing our discussion next week. Make sure you get that progress assessment to me. But other than that, have a great day, have a great weekend, and I'll see you guys later. Next Tuesday is the next time I see you. Bye, everyone.
Have a good weekend, Mr. Giorgio.
See you later. You too.